You're right.
But isn't its main isotope also naturally decaying as it produces radioactivity? Like
Yeah, and then
238.
it makes a bunch of other radioactive isotopes as well.
I remember when I was when I was researching fission, there's a special isotope of uranium that's used instead of the naturally occurring stuff. In order to make it, you basically have to sift through uranium. It's like 236 to 238.
Oh, okay. Yeah, there are a lot of different isotopes. I don't know which particular isotopes. Like here, okay, here it is obtained by bombarding bismuth 209. So bismuth, you can take that with neutrons, which makes bismuth 210, which then decays to form polonium. All the commercially produced polonium in the world is made in Russia.
Okay, go to Russia.
Yeah, you can go to Russia.
Yeah.
You can buy it on the black market.
Yeah, I was going to say.
I'm
You
pretty
can
sure if I go into
find
a
it if
research
you
facility,
try
I could buy it more legally.
Yeah.
But
It's out.
did you hear? You know, I mentioned this before. The polonium, LAX.
Oh, yeah, the polonium poisoning.
Right.
Oh.
Yeah. Like dozens. Oh, they didn't include it. Where is it?
It's been the whole
Yeah. It was in LA. There are 2 people coming back from Russia who were poisoned. And then this one, the Russian spy Alexander Litvinenko
Oh wow, that's mine.
in London.
Oh, that's horrible.
He died of radiation sickness. This is bad. They actually have pictures of his deterioration. They couldn't do anything for him. Yeah, that's pretty sad.
Watched a video about this.
Right. Okay, were there any other questions, Chad?
I know my question.
All right, so we were leaving off talking about the mole. Whenever we talk about the mole, the way it was defined was based on the U. And so we had the U was 12. U was the mass of a carbon-12 atom or nuclide. And the mole, they just take 12 grams to be exactly 12 exactly 1 mole of carbon-12 atoms. And so this would be 1 carbon-12 atom. And then the next thing is, how many carbon-12 atoms are there in 12 grams of carbon-12? And that's where we get Avogadro's number. Good, 6.022 times 10 to the 23rd.
I have a question about Avogadro's numbers. For the significant figures, should we go 4 or 5 after?
I don't know if this has been updated yet. This is 4 sig figs. But they're thinking of converting this into an exact number because I don't know why, it's just more convenient. And so this is Avogadro's number, ANA, Avogadro's number, which gives us some interesting relationships that we can figure out. How many U are in a gram? You know, when I was in physics, I memorized how many grams are in a U. 1.67 times 10 minus whatever, I forgot it. Because it's much easier to remember how many U are in a gram. Do you know how many U are in a gram? So if you have 1 gram, how many pieces would you have to divide that into to get 1 U's worth of mass? And so it's easy to remember because it's Avogadro's number. You have an Avogadro's number of U in a gram. But it's also easy to derive using dimensional analysis. So one of the key relationships is the U to gram conversion. And so this is not difficult to do because we start off with 12 U per carbon-12 atom. And then we know that there are 6.022 times 10 to the 23rd carbon-12 atoms in a mole of carbon-12. And so the carbon-12 atoms cancel the carbon-12 atoms. and then we just get rid of moles. Then we know that 1 mole of carbon-12 atoms weighs exactly 12 grams. And so the moles of carbon-12 cancel, and the 12s cancel, and what this gives us is it gives us 6.022 times 10 to the 23rd U per gram. And this goes for anything, not carbon. It doesn't have to be carbon-12. It's for any substance. Although, you know, there's nothing that weighs exactly 1 U. So U is extremely small, obviously. I mean, if a gram. Some people say, do you know how much a dollar bill weighs?
What's the
How many grams does a dollar bill weigh? Let's see.
Here, Chris, you have a scale on
No.
Now I'm thinking, has the weight of a dollar changed since
they print more.
Those kind of things.
Okay, here it is. It weighs about
Oh.
1 gram. So a dollar bill weighs about 1 gram. So if you take that dollar bill and divide it into 1,000 pieces, each piece would weigh
1,000.
a milligram. If you take that dollar bill and divide it into 1,000,000 pieces, each piece would weigh 1 microgram. If you take that dollar bill and divide it into an Avogadro's number of pieces, if you can even visualize that, that would be too difficult because it'd be smaller than an atom, then each piece would weigh 1 U. Yeah, so that gives you some kind of way to visualize it. Or you could do it with a $100 bill. Does a $100 bill weigh more?
I would think it would because it has more in it. It has a strip, right?
Yeah, it has that strip and
It
has
has
this
the strip
That's what
and
we
the
should
two
have done
magnetic
instead of
strips.
weighing pennies.
Yeah, probably.
We should have weighed different bills.
Get one of those like prop bills that they have. Go down to the theater department.
All right, so we're going to use this in calculations. This is dimensional analysis. I mean, just more dimensional analysis. So what would be a problem? Dimensional analysis, chapter 2 style problem. A dimensional analysis, chapter 2 style problem, we'll just make one up, would be if I had like a cup of water, let's say more than a cup. If I had, actually, how much is a cup of water? Is it 16 or 8 ounces? 12 ounces? Is it 12 ounces in a cup?
A cup is
Four.
8.
Yes, it's 12.
1 cup is 8 ounces?
Yeah.
All right.
1 cup is 8.
So in 1 cup of water, actually, how much water do you drink? 1.5 cups, 2 cups worth?
What?
Well, we'll just go with 1 cup.
Let's say I have-
Day?
No, just let's say if you're thirsty.
Okay.
I drink actually much larger. I have
Yeah.
32 ounce.
This is
let's say
50, so
32 ounce,
fine.
4 cups.
All right, well, let's say if you have 1 cup of water,
This is just a liter.
in one cup of water, how much of the heaviest water molecule? What was the heaviest water molecule?
It was the heaviest had to be
H2O18 H2. Or in terms of mass number, combined mass number would be what?
22.
22. And so how much of this did you just drink in a cup of water?
Like less than 1.
It's ambiguous that way. So we could say grams, we could say U, we could say what? Molecules, we could say moles. You know? And so it's ambiguous, so you just pick, if it's not stated what they want you to calculate, then you pick something. You know. Some people might say, oh, there's not enough information to solve because you didn't tell us what to solve for, but you'd have to just assume that what you're interested in is what they're interested in. Because so if you have a question, if you're giving a talk or something and you have a question from the audience, the question from the audience might be, how much? They might not specify, so you might ask a follow-up question or you might just answer it different ways. And so this is dimensional analysis, I think. So we'll just start off with 1 cup of H2O. And from 1 cup of H2O, where can we go?
Can we go from cups to ounces to milliliters?
Do you know the conversion from ounce to milliliters?
No.
Then let's not go that way.
We can go from cup to liter.
1 gallon equals 3.7.
Do you know the conversion between cups and liters?
You know cup to
2 gallons a liter.
Do you know how many cups are in a gallon?
Yeah,
Right.
16.
16 cups in a gallon? What's one that you for sure know that you don't have to worry about at all?
I don't think I know what you're right.
We could go cups to pints or cups to quarts.
Oh.
Do you know? Well, we'll just go. There are 2 cups in a pint. A pint is 16 ounces. And then we can go from pints to quarts. Everybody should know how many pints are in a quart. 2 pints in a quart. And then how many quarts in a gallon?
4.
Yeah. Okay, so this one we don't have to worry. I mean, it took us extra steps. I mean, if I had how many cups are there in a gallon? That's 2 times 2 is 4 times 4 is 16. 16 cups in a gallon. So if you have that memorized, then that's fine. You know. If not, then just go with the ones you have memorized. All right, now where can we go? Gallons to liters. Does anybody remember how many liters are in a gallon? 3.785. If you forget it and it's not given, then you just say, you know, a liter is about a quart. It's going to be much more qualitative. But, you know, if we forget this, then we might say 4 liters in a gallon, roughly. But that's only good to how many sig figs? 1, and it's going to limit the precision of our final answer. But that's all right. It's better than leaving it blank. You know, some people will go, I forgot it. You know, therefore I can't solve it, and therefore I'm just going to not know. So if we don't have the number, we just try to estimate it, you know. It's better than nothing. Any answer is better than nothing. All right, now we have liters of water. Where can we go next?
Milliliters.
Milliliters, that sounds good. Go 1,000 milliliters to liters. Now we have milliliters of water, then where? Probably grams. Okay, but in order to convert milliliters to grams, we need to know the density. Do you know what the density is? And to how many sig figs? Well, we could say it's 1 gram per milliliter, but that's only 1 sig fig, so it's kind of limiting.
Could we use 0.998 at 4 degrees Celsius?
No, it's not.
No, not 4 degrees.
It's
5
not 4 degrees Celsius. In fact, we need to know the temperature, right? In order to get a precise density, we need to know the temperature. But we don't have the temperature because the person who asked never gave us a temperature. And so some people will stop here and say, oh, the temperature wasn't given, therefore I don't have to solve it. You didn't give me enough information. But again, you know, people don't expect that kind of answer. People expect you to take a guess, at least, or at least know roughly what it is. And so could we be more precise? And so this is it. We don't memorize tables like this. There's a $100 bill. Loan in. We don't memorize tables like this. You know. What do I look here? Let's try this one. Hopefully this one will be okay. But what we do is we try to just get an idea of what the densities are. You know, this one's not as precise as the one in the lab. The one in the lab had 6 decimal places. This one only has 5 decimal places. But let's say you would predict it's around what? You know, if the temperature is not given, then you just assume it's going to be what temperature?
Room temperature.
Room temperature. And what is room temperature?
22 to 24 degrees Celsius.
That's normal. That's comfortable, but that's not the room temperature that.
Is that
25. 25 is a bit warm. I don't like it, but that's room temperature. Room temperature is 25. I wouldn't set it that high, unless it's a cold day. If it's a cold day, I'd set it that high. You know, because 25 is like 77, 78, isn't it?
that's too high.
It's too high. It's uncomfortable. But when people talk about room temperature, they're typically talking about 25.0, and the density is 0.997. So are you going to memorize that? Probably not. In fact, how much does it change? Well, normal room temperature, well, unless you're in the lab. If you're in the lab, it's more like 16. Wasn't it like 16 yesterday?
My water was like 19
It
degrees.
was 19? Okay, maybe a little warmer than I thought. So like 19? At 19 is a little more dense, 0.998. You know, at 25 is 0.997. So we don't know what the temperature is, so since no temperature is specified, we're just going to call it what? Maybe, let's do maybe 2 sig figs. I don't think we can go 3 sig figs. So 2 sig figs, what would it be? 1.0. And so what we're going to do is we're just going to assume 1.0 grams per milliliter. And this should give us a pretty good range of temperatures. And the 2 sig figs. And so now we have grams of water. Next, what can we do?
You can go from grams to
Grams to moles.
yeah, grams.
And so we need the molar mass of water. And so the molar mass of water, we're just going to take the average of all the water, you know, of the weighted average of all 9 water molecules. And in other words, we're going to use the average hydrogen. The average mass of a hydrogen is 1.0. I usually go 2 decimal places if I'm calculating compounds. If I'm doing elements, for hydrogen, I'll go 3 decimal places, 1.008. Oxygen, the average mass is 16.00 to 2 decimal places. And so we have this times 2. And so I get 18.02. Now, this is why the mole is defined in a weird way. The reason the mole is defined in a weird way is because we can use 2 different units with this. One is the average water molecule was 18.02 U per water molecule. Or a mole of water molecules will weigh 18.0 grams per mole. And so actually, you know, defining the Avogadro number in such a weird way makes our life a lot easier in terms of calculations. And so we aren't looking at a specific isotope. We have 250 milliliters. No, actually, I don't know how many milliliters. How many milliliters is a cup of water? Around 200 milliliters?
236.
236 milliliters. Okay, then that gives us the moles of water. So we have 18.02 grams per mole of water. Okay, then we can do different branches here. The percent natural abundance can have multiple units as well. Did we calculate the percent natural abundance of H2O18 and H2?
Yes. That's
The other day we were looking at,
This,
or was it on a chart, maybe?
all right. I guess we could calculate it again. The abundance of this is going to be deuterium. Deuterium is a 0.0115 out of 100. O18 is a
it's like 17.999.
over here.
Oh,
0.205 out of 100. And then H2 is just going to be 0.0115%. And this gives us a percent abundance of H2O18, H2 as 0.0115. So I'll convert this to decimal, 0.0001115. 0.0001115. I'll convert this to decimal, which would be 0.00205 times 0.00205 times 0.0115. 2.71. We're allowed 3 sig figs, so I'll just carry one extra. 2.711 times 10 to the minus 9%. Is that what you guys get? I might have gotten a different number last time. I don't know. Yeah? No?
Yeah, I got 2.711 times 10 to the negative 9th percent. Wait, yep, percent.
Okay, thank you. What is this percent called?
Percent abundance?
Yeah, percent natural abundance, but what type of percentage is it?
All over.
Percent by mass? No. What is it? What is it?
Quantity.
Percent by mole. When you see percent by mole like this, there are different ways we can write that. If you see a percent by mole, what this means is 2.711 times 10 to the minus 9 moles of H2O18H2 per 100 moles of what?
H2O.
H2O. So this is the classic mole percent. Or it could be a molecule or atom percent. And so it could be, because mole is just a counting unit, and so, you know, if I had a dozen, you know, I could say a dozen of these and 100 dozen of those, you know, or whatever, 2.711 times 10 minus 9 dozen. And so what we can do is we can just go all the way to a molecule. And so we can say 2.711 times 10 to the minus 9 molecules of H2O18H2 per 100 molecules of H2O. And so it could be molecule or an atom percent. So in other words, a mole percent is the same thing if we're dealing with molecules as a molecule percent. But what if we don't have molecules? What if we're just dealing with atoms? Then it's the same thing as an atom percent, which is the same thing as a formula unit percent, because not everything forms molecules or atoms. So there are different branches here. We can go ahead and use the mole percent here, but we're not. What we're going to do is we're going to convert this to Avogadro's, using Avogadro's number to molecules. And so 6.022 times 10 to the 23rd H2O molecules per mole of H2O molecules. Okay, now we'll just use the molecule percent here. And that is, we're going to have 2.71 times 10 to the minus 9 molecules of H2O18H2 per 100 molecules of H2O. Okay, so let's see. In that cup of water, how many molecules of this do we have? So let's go ahead and calculate it. Take 1 divided by 2 divided by 2 divided by 4 times 3.785 times 1,000 times 1 divided by 18.02 times 6.022 times 10 to the 23rd. I didn't bring my calculator. Something's wrong with my phone calculator. Can't do scientific notation. Oh, well, anyway, did somebody calculate it?
Almost done.
There you go.
I got 2.10844 times 10 to the 14.
2.018
2.10.
2.10844
Yeah, 44 times 10 to the 14.
times 10 to the 14. Well, my calculator's not working, but we can do an order of 10 to the 23rd times 10 to the minus 9 gives us about 10 to the 14. And then we can look at the numbers.
About the same.
You got it about the same?
And to two significant figures.
And then to two significant figures, it would be,
Oh wait.
how many sig figs are we allowed?
Is it 2 because of grams H2O, or is it 3 because of 2.7?
What if here's the density of water? It's good.
I'm sorry?
The density of water. So
There's 2?
Yeah.
Yeah, it'd be this one here. Or isn't it 1?
I think that you can be exact on that.
Yeah, on this one we could be exact. And then just put all the uncertainty in the other term. Right, so in exactly 1 cup, approximately how many? And so what we'll do is we'll just round this to 2. It's 10 to the 14. So let's see, 10 to the 12 is a trillion, right?
Yeah, so
And
it's
so-
100 trillion.
210
Yeah.
times 10 to the 12. And so 210 trillion. And we could do the combined mass number, H2O 22s. So you had 210 trillion of those water molecules in there. That's a lot. Doesn't seem like a lot? Seems like an awful lot. So you know, there's that video. I told you about that video, right? Can you drink heavy water?
It tastes like calcium.
Heavy water actually has a density of
Heavy water is also known as deuterium oxide. Okay, deuterium is an isotope of hydrogen with an atomic mass 2. The density of deuterium is higher than hydrogen. Drinking heavy water in small quantities does not harm, but drinking in larger quantities for a prolonged period can cause dizziness and low blood pressure. Well, I don't know what, is this reliable? I don't know.
Didn't you say you used
No,
to
I don't
drink
think it's
heavy
reliable.
water?
I know, I used to use it. I used to buy bottles of this. Have you ever seen this guy?
No.
This guy has a lot of interesting videos
I
on
like
the
his
elements.
hands.
Yeah, this is, you know, the prototypical, like, eccentric
Uh-huh.
scientist here. So,
I'll go down to Science Notes post.
Yeah.
The more reliable source.
Oh, nah, this guy.
I would trust an organization more than I would trust a commercial website.
yeah.
This is super super good.
That's why I use Bing.
Well, unfortunately, there's no audio. Here's some deuterium. It looks like water.
Capsules.
Tastes like water.
How does he have that
A little bit heavier. But if you're interested here, he produces a series called periodic videos. And it's pretty interesting. Actually, he talks about polonium too. If you're interested in polonium, check out his videos because he's a PhD in chemistry, so he can explain it pretty well.
I feel like Einstein's hair would be bigger, but I totally see it.
But to put this into perspective, how many grams is this? How many grams of water?
That's less than one.
Oh, it's 236.5625.
Oh, you already calculated?
Yeah.
Wow. And what did you use?
I calculated it at the beginning when we had grams of H2O. Oh, different H2O?
H2O. Oh yeah. Okay. That's the total H2O. But how many grams of the heaviest of the heavy water did you drink?
It should be less than a gram because Avogadro's number is 6.022 times 10 to the 23rd U per gram per mole. So if we have 210 trillion, which would be 2.1 times 10 to the 15th, it should be less than a gram.
Yeah. So what we'll do is we'll just go ahead and calculate it. Let's calculate it. How should we calculate it? Well, we could calculate it here. I know how many H2O22 molecules I just drank. So I could figure out the mass of an H2O22 in U per molecule. You know, I have two different choices here. If I have an H2O18H2, I know the mass of an H2 is 2.014102. That would be these two. And the mass of an O18 is
17.999 something.
good. That was pretty good memory there. 17.999 something. And then something is
160.
160. Okay, so let's just add it up. So that's going to be 2 times 2.014102 plus 17.99916. And so this has a combined mass of 22.02. Now I got to figure out how many sig figs am I allowed? Yeah, all of them actually. 22.027364. I'm going to be allowed 6 decimal places. Now, I have a choice here for the units because of the crafty way the mole was defined. And so what are my choices for unit for this? U or grams. And so in terms of U, this would be 22.027364 U of what?
22 H2O or
Well,
2
we could just say U per what?
Well,
Yeah, per H2O18 H2 molecule. So a single molecule of this weighs that much. What was the average mass of water that we calculated? It was 18.02. Could we find a molecule in nature that weighs 18.02 U? Does such a molecule exist? No. And so and the reason is if you're working with large quantities like a cup, then you don't want to look at individual isotopes. What you want is you just want the average. So we get the average here. But if you're looking at single molecules, then it makes no sense to use this mass at all because there's no single molecule that weighs this. And so when we're looking at single molecules, we have to know which molecule we're looking at and how much that particular molecule weighs. And so It depends on what scale. If you're working at the particulate level, then we're always going to be looking at the isotopes. If we're looking at the macroscopic levels, then we just look at the average. And so this would be at the particulate level. We have one of these molecules that's going to weigh this much. Well, that's good for us because we have 210 trillion of those water molecules. And so the calculation that I would do here is if I have 210 trillion, or 210 times 10 to the 12, of these molecules, then I can just use dimensional analysis to calculate the mass. And so the mass, it's going to be 22.027364 U per H2O18 H2 molecule. And that tells me how many U. But you know, if a dollar bill has an Avogadro's number worth of U, then U is very hard to visualize how big that mass is. And so probably rather than using U, I'd probably be more comfortable with what? With grams. And so what's the conversion factor here? I want to convert it to grams. I've got to get rid of U, so what's the conversion factor? 6.022 times 10 to the 23rd U per gram. Because this is going to tell me how many grams of H2O18 H2 I have. And so, can somebody calculate that? No.
Times 10 to the negative 9.
So, is that what other people got? So 10 to the negative 9 is called what? Nano. And so this would be, and we're allowed 2 sig figs, 7.8 nanograms. A nanogram, the way to visualize a nanogram is you take a dollar bill and divide it into how many pieces? Not that, not a trillion, a billion. If you take a dollar bill and divide it into a billion pieces, that would be 1 nanogram. And so nanogram, well, that's how much heavy water you just consumed in that cup. That's how much it weighs, 7.8 nanograms. Alternatively, we could have used the mole, 22.027364 grams per mole of H2O18 H2. If we use this conversion factor, then we would have had to do it earlier in our chain. The advantage of using this is that people sometimes forget this conversion. Because when I forgot this conversion many times because when you look at the conversion, when you look up the relationship between the U and the gram, and I don't understand why they always do this, and this is a conversion I had to memorize. I should say AMU and the gram relation. This is the one I remember. In physics, this is the one I learned. 1 AMU is equivalent to 1.66 times 10 to the minus 24 grams. And that's what's in all the books. In all the books, it's 1.66 times 10 to the minus 24 grams per U. And so the disadvantage of knowing this one is you'd have to remember the conversion from U to gram. The advantage of using this one is you don't need to know the conversion from U to gram. But the conversion from U to gram is so simple that if they would have taught, it's because it's physics. Or maybe a lot of physicists don't memorize Avogadro's number. Did you have to memorize Avogadro's number in physics? No. And so they probably don't care, you know, to minimize the amount of memorization you have to do. But look at, does anybody show it the other way? Look at this one, 1.660538886. That's pretty precise. Oh, here somebody did. That's good. 6.0229552899499 times 10 to the 23rd. But that's the old Avogadro's number. Let me see if they've agreed on Avogadro's number. They're talking about making an exact number. We need a recent article. Maybe it hasn't been done yet, so it's all right. The exact definition of mole is based on the Avogadro number. They don't say if this is exact. All right. Oh, here they do. Na is exactly equal to 6.0221407.6 times 10 to the 23rd. This is not really exact, but they're just defining it as exact.
Yeah, they say that's no longer based off of the carbon 12.
Yeah. Okay. All right, so this is an example of using the mole concept and isotopes and that kind of stuff. So what we're going to do is we're going to move on to chapter 3.
Could we go back to the tab with AMU and grams?
AMU and grams?
Yes. I wanted to copy down the gram.
Okay, like this?
Yes.
Physicsforum.com, is that reliable? Most people don't do it to this many digits. When I learned it, I did it to 366, 1.66 times 10 to the minus 24. That's what most people do.
If it's for exact measurements or something like that, I do not trust commercial websites for something like that.
Yeah.
I would more go to something that says .org or .gov. Because that would be more reliable.
Right. NIST is a good source for this. You guys are familiar with NIST?
Yeah, what is NIST?
NIST, I saw an interesting video about NIST. NIST stands for the National Institute of Standards and Technology. And they try to maintain all the standards. Like, you know, I guess the equivalent would be like in Paris, France, where they have the kilogram locked up. Well, if we had the actual kilogram, it would be locked up at the NIST. But the interesting, you know what the interesting video I saw was?
What?
Peanut butter. They have a standard for peanut butter. And yeah. And
What is the standard?
the standard for peanut butter, okay, you know, there should be a certain amount of fat, there should be a certain amount of protein, and then they break it down by compound by compound. Since they completely analyze a sample of peanut butter and figure out how much of everything is in there, this is a calibration standard. So if you make your peanut butter, you can calibrate it against this one. Or if you have instruments, you can use this peanut butter to calibrate your instrument so that when you check your peanut butter for how much fat and whatever, or how much this fatty acid is in there, you can determine it.
That'd be pretty helpful.
But that jar, don't eat that NIST peanut butter because one, it's so old. I think they said it's like 20, 30 years old. It's been sitting on the shelf. It's not a high volume item that people buy. And then number two is that jar of peanut butter is like $16,000 or something.
That's gonna be one really good PB&J sandwich.
Really bad one.
I'm gonna make my own jam for that.
Yeah.
Different than the standard.
But they have it here, the atomic mass
No, I wrote it down.
from This is from the NIST, physics.nist.gov. So,
It is down to a very specific down to a very specific kilogram.
yeah, that's pretty good.
Very small thing.
All right.
Sorry to interrupt.
So NIST is very reliable. They spend a lot of their budget is in the billions of dollars per year.
Oh, that's actually pretty good.
Yeah. So they're wealthy government department or whatever you call that.
That's why it's supposed to make money. Not much happens outside of this country. Yeah, we don't really need most of the budget
Yeah.
going to places.
Yeah.
But
So
it's fun to put it there. We get new toys out of it.
yeah, I'm sure they have access to a lot of nice toys there.
What if they have a scale that measures to like the 10th place of gram, something so utterly precise?
No, the research labs are cutting edge. NIST is probably not cutting edge.
I wonder what is it, most like sensitive scale is then? Like how many decimal places past the gram would it go?
The old mass spectrometers didn't go that many decimal places. So, you know, there was a running joke. You know, in like academics, you have to publish papers to survive. And so the running joke is, you know, all you have to do is build a more sensitive mass spectrometer, and then you're guaranteed a publication. And so it's so easy. And so the electronics get better. It's, you know, technology gets better. You're guaranteed. All right, we're going to look at chapter 3, chemical compounds, next. Chemical compounds. When we look at elements, you know, there are different structures for the elements. Some elements are just atoms, like helium, neon, argon. If you have a sample of helium, it just consists of helium atoms. All the noble gases just consist of atoms. Gold consists of atoms, but they're bonded in together in what we call metallic lattice. And so most of the elements, you know, because if you look at most elements seem to be metals, don't they? I mean, the metals are to the left. Here's the borderline. The borderline we call what? Like polonium.
Metalloids.
Metalloid. So polonium would be a metalloid borderline. But the metals, they form metallic lattices. You guys are familiar with lattices? Okay. And so the gold and platinum, palladium, they all have the same lattice. And so a lot of the properties are quite similar. They're quite malleable. It's because of the way they bond together. Magnesium has a little different lattice. And so it's not quite as malleable. It's a little bit more brittle than some of the others. But you know, there are a number of different lattices that you see. And then when we look at the nonmetals, most of the nonmetals are going to be different types of lattices, or different. There's going to be more variety in the structure for those. And sometimes we see molecules, sometimes we see chains, sometimes like polymer style chains, or sometimes we see lattices. But you guys know the diatomic, the 7 diatomic elements. When we look at compounds, we categorize compounds often based on their structure. You know, so what types of compounds do we have?
Lattice.
We have lattice compounds. We have some are called ionic lattices. Have you heard of that? Ionic lattice for ionic compounds. And we have covalent lattices. Ionic lattices would be like sodium chloride. Usually when we have an ionic lattice, it consists of ions. And ions are going to consist of cation and an anion. And so typically when we have cations and anions, we're looking at metals. Metals, the elements on the left side of the periodic table tend to gain electrons, they tend to lose electrons. So the metals on the left side form cations, and the elements on the right side tend to gain electrons and form ions. So when we have a metal and a non-metal, it's usually ionic. Ionic compounds form ionic lattices. What if we have a semi-metal and a non-metal? Like silicon and oxygen. Silicon's a semi-metal. Oxygen, what type of, is that going to be an ionic lattice? No. That would probably be a covalent lattice, and it is. Silicon and oxygen form quartz. And quartz is a covalent lattice. Some of these, like phosphorus and oxygen, form molecules of ionic. And so when we get metal and non-metals, we get ionic compounds. Semi-metals and non-metals typically form like covalent lattices, covalent compound. And non-metals plus non-metals form molecules usually.
They form ionic, right?
Which one?
The ionic compounds?
Yeah. They form,
Or ionic bonds,
they form ionic bonds. Yeah, exactly.
in simple terms.
Right. And so ionic bonds. And so types of chemical compounds, those are the types of chemical compounds. The mole concept and chemical compounds, well, I jumped ahead. I did that for water already. So I'm going to skip that. We're going to look at the composition of chemical compounds and oxidation states next. So, actually, this is. Did you know? You know, California is a very active state. You know, California, they're going to require all automobiles to be electric by 2036, and probably in LA and in San Francisco. Are you going to have any more gas appliances in new construction?
New construction now.
No. No more gas appliances in new construction. Although places like Panda Express and those might find it difficult. I hear a lot of chatter about that.
McDonald's and their magic gas stove.
And then like, you know, the flame broiled hamburger? What are they going to do now?
Well, they can use charcoal.
Flame broiled. You know, although they have these, you know, the electric flames. Have you seen those? Electric flames, like those faux fireplaces. These are just optic. These are fake fireplaces, but they radiate a lot of heat.
So good.
Yeah,
Oh,
We love those.
yeah, that's nice.
my dad has one of those. You know, it has a special remote.
So it could be like the you know, optical flame broiled
Optical
charburger.
flames, like the purple ones?
Yeah. What's that?
Like optical flames, like the purple ones?
No, it doesn't have to be purple. It could be. It could look totally natural. In fact, I saw one that looks totally natural and radiated a huge amount of heat. It's pretty cool. It's like flat. It was like a laptop, and you open it, and then you turn it on, and then it's just blasting heat at you.
So cool.
It was pretty cool.
I think the funniest experience I've had with electric furnaces is that normally the remotes they have are all a generalized radio frequency. So I've been able to turn it on with like random controllers and remotes around the house.
That's dangerous.
So
Actually.
it's quite funny when you go to turn on the TV and your fireplace kicks on.
Yeah, that would be pretty. They're going to have to control it some way.
Yeah.
But anyway, there's another thing that California is a pioneer, or what do they call it? You know, and one of the things they are going to do, I didn't know this, but I just read this. You know, PFAS. Have you heard of that? PFAS. By 2019, it's going to be banned. Maybe you don't care. Maybe you care.
So within the next 6 years.
Yeah, the California ban is anything containing PFA.
Prop 65.
Let's see.
Oh.
The food packaging takes effect in 2023.
Oh, that's
already
year.
happened.
Already happened.
Yeah, that already happened. But they're going to ban it in everything. And that's going to take a little bit more time because they're going to ban it by California bans PFAS in textiles, cosmetics, but governor vetoes requirement. But basically, it's going to be banned in every single thing. Beginning January 1st. Oh, this is textiles.
2 years from now.
Anyway, so what are they? They're a class of compounds that contain carbon and fluorine and some other stuff. And there are a whole bunch of different ones. But, you know, have you dealt with any of these? And I've been thinking, yeah, probably, because, you know, it's raining. And so a lot of clothing, like, you know, they call weatherproof clothing. Probably this is weatherproof. My pants probably is loaded with it, maybe. But it's water repellent, and so a lot of water repellent sprays and that kind of stuff contains this. It's like a Teflon coating for your clothes, basically. But they use it in a lot of different things, and so it could impact you. But anyway, they're going to ban it. But the thing is, there's so many different ones. And so if we go and if we're thinking about, like, you know, chemical exposure, you know, how do you get an idea of well, the first thing we look at in terms of chemical exposure, you know, why are they banning these? And so at the first level, we probably would look at something called the SDS or the MSDS. Do you guys know what that stands for? SDS, MSDS?
Safety.
Safety data sheet. And MSDS stands for Material Safety Data Sheet. The MSDS, you know, we have a thick binder. It's a thick yellow binder inside the lab. Every single chemical you purchase has to come with an MSDS. And it tells you what to do in case, you know, in case of fire, in case of contact, in case of whatever. And so whenever we get a chemical, the first thing we do is we just read through the MSDS or the SDS. The MSDS, I don't know why, but they, maybe about 5 years ago, they said, okay, we're going to switch from MSDS to SDS. Why? I don't know.
I think it goes faster to write. So one thing.
Somebody had a reason, but anyway.
I'm curious that reading the hazard was identification. It says that it needs to be disposed of by high temperature incineration for polyfluorides.
Oh, this is probably the wrong one. Yeah, high temperature incineration.
I was about to say that's interesting because I imagine that the vapor that comes off of it would probably be pretty bad.
Yeah. Yeah.
If it's carbon.
Well, we'll talk about incineration and combustion also in this chapter. So PFAS, what does that stand for, first of all? It stands for polyfluoroalkyl substances. Fluoro just refers to
Fluoride.
fluorine. We don't call it fluoride in organic compound. Alkyl is, you know, alkyl, have you done any organic? You have the alkanes, the alkanes, alkenes, and alkynes. Have you ever heard of those? The alkanes are all single bonds, carbon and hydrogen. Alkenes will throw a double bond in there. Alkynes will have a triple bond. And so these are just organics. Poly just means many fluorines in there. And usually what happens is the fluorine substitutes for hydrogen. And so you've heard of per before. What was the per prefix used for in the past? Like perchlorate. And why do we have perchlorate? What did the per refer to? We had hypo at one extreme and per at the other. You know what those hypo? Have you heard of hypo before? Hypo means less, low. Yeah.
Usually
Hypo, like hypothermia. Hypothermia means you're too cold. Your body temperature is too cold. Hypothermia. At the opposite of hypo is per or Hyper. And so hyper, this could be hyper or poly. Hyper, in reference to hyper, that means probably it's completely saturated with fluorine. You know? And so that's what. And so typically we see per. This means the extreme at one end there.
I have a question, sir, about the fluorine. Is it poisonous to touch as it is as a PFAS?
Do you brush your teeth with a fluoride toothpaste?
I do, and I can't ingest it because it's poisonous.
Yeah, don't ingest it, but you're still here.
I was about to say it should be poisonous to the touch, but as a PFAS.
As a PA, do you cook in a does anybody cook in a Teflon coated pan? You've touched it. You've touched it.
Can I cook it with olive oil?
Olive oil doesn't have any fluorine, so you're safe.
All right.
Cook with toothpaste. There you go.
But yeah, it depends. There are reasons for this. It's not the fluorine. Fluorine's very hazardous, and there are different types of fluorine. You know, we have fluoride, we have fluorine gas, the element, and then we have fluorine in organic compounds like this. The reason that like Teflon coatings are so strong, you know, and so unreactive is because the carbon-fluorine bond is so strong and unreactive. Whereas if this were a carbon-hydrogen bond, that carbon-hydrogen bond would be a lot more reactive. Yeah, and so, for example, fluorinated and chlorofluorinated compounds that were complete. When I was at UCSB, there was a group that was looking at using CFCs for synthetic blood, artificial blood. And the reason they were looking at using CFCs for artificial blood is because the bonds are so strong, they'd be unreactive. And they shouldn't cause much trouble, and then they can transport things. They use CFCs in refrigerators, you know, for many years, thinking that this is perfect because they're non-flammable. CFCs, you can't burn them, whereas hydrocarbons you can burn. So if you had something like this versus something like this, methane is very flammable, but carbon tetrafluoride or fluoromethane is inflammable. You can't burn this stuff at all. It's totally stable. But like a lot of these things, you know, the longer term effects are hard to predict. You know, if you look at the theory for chemistry, what was the theory of chemistry? The theory underlying chemistry? Quantum mechanics. If you look at the math for quantum mechanics, the math is so difficult that the only thing that you can solve exactly is the hydrogen atom. If you go to helium, then the math becomes too horrendous and you have to use what are called approximations. When you use approximations, it's like approximating the density of water. Is your answer going to be so accurate and so precise? No, so there's going to be added uncertainty. And so as these things get more and more complex, you know, systems, it's hard to predict, you know, what the longer term effects are going to be. And so CFCs are now banned. You know, at the time they thought they were the wonder chemical because, you know, non-toxic, non-flammable, perfect for refrigerators. But now we know that there are reactions that weren't foreseen, that weren't predicted. And that's because modeling, it's like trying to model the weather. You know, if scientists are so great, you know, why can't they predict the weather to a high degree of precision and accuracy? Well, it's the same thing, you know. When you get into natural systems, it becomes very complex. It's hard to predict. And so, anyway, so the first thing is there are lots of different CFCs, and the CFCs are going to have different impacts. This is like, have you heard of what is it, Palestine, Ohio?
Yes.
Yeah, the chemical spill there. Yeah, that was pretty grim there. I mean, vinyl chloride. I don't know how many tons of vinyl chloride spilled into the water. You know, and then they were saying, okay, the EPA has designated 1 part per million as acceptable. But you know, when you look at that water is going to be way more than 1 part per million vinyl chloride in there. I mean, you could drink it once, and I saw them drinking it, and I thought, okay, yeah, once. But if you're drinking it day in and day out, that's a different story. But anyway, what we want to do is we want to look at specifically what the chemical is. And so if you want, you know, this is the SDS. This is very broad. They were saying when they were sampling, you know, there are 2 ways that they recommend sampling. One way is they take an air sample or water sample and they seal it into a container. And then they take this container to a mass spectrometer and then feed everything in the mass spectrometer and see what's there. You know, that's what they... Or they have this little detector. The little detector just detects how much, you know, organic is in there. It doesn't tell you what it is. And so they're saying, well, it's safe according to this, but that's very crude. What you want to know is what exactly is in there. What are the compounds that are in there? You know, they try to incinerate it, but they, you know, if you do incineration, you need high temperatures to make an accurate prediction. Because if you have low temperatures, and even here, can you tell me under what conditions you're going to get carbon monoxide? You know, how do you adjust this? I want to maximize the carbon monoxide, let's say, and because of some reason, you know, tell me the optimum way to make the most carbon monoxide. Can you predict how much carbon monoxide? I'm going to get 80%. I want 80% carbon monoxide, 20% carbon dioxide. Can you tell me how I'm going to do it? Do you think that's an easy thing to calculate? No, and so a lot of stuff we just do it and see what happens, and then bottle it. But to prevent things, unwanted things from happening, that's why we use high temperature. Because if you use high temperature and lots of oxygen here, then what should we get? We should only get CO2, and then we can predict it because complete combustion will give us CO2. But you know, when they did the incineration there, you know, that was low temperature and lots of black smoke was coming out, and who knows what they formed. Well, actually, I looked at vinyl chloride. They did a study on vinyl chloride from, I think it was from 900 to 1200 degrees C. And the main product of vinyl chloride combustion was hydrogen chloride gas. Hydrogen chloride gas with water will make HCl. And so they're saying that was the main, and then some minor components was like phosgene gas. Have you heard of phosgene gas? There's only like 12 ppm phosgene. Phosgene was one of those chemical warfare agents back in...
Like mustard gas?
Yeah, like that in World War I. And so that's probably what killed the animals, you know. The HCl and the phosgene is probably what killed the chickens or whatever they were. But hopefully that disperses, you know, and we're okay. I mean, eventually those things break down, the HCl and the phosgene. But it would be nice to know, you know, exactly when they did that incineration, what the heck did they form? You know, because they formed a lot of things, including soot and lots of other chemicals. And so this brings us up. Okay, they're going to form a mixture, and what we do with the mixture is we try to separate it into substances. This is the great thing about mass spec. There's something called if you hook up what we call this is an experiment that I did when I was a student at UCLA. It was using something called the GCMS. And so what we did was, this was an upper division lab in chemistry at UCLA, and we just got samples to feed into our GCMS. So I got a sample of gasoline, like super unleaded and then regular. And then looked at, this was from, let's say, Chevron, and then I got one from Shell. And then fed it into the GC mass spec. The GC mass spec, what it can do is it can tell you everything in that mixture and how much. Because the first part of the GC mass spec, it goes through what's called a gas chromatography column. And these columns, they have different resins and different packing in here depending on. And a lot of them are like aluminum oxide, silicon oxide and stuff. And so you put a sample in here. And some molecules interact more strongly with the column, others don't. And so the others that don't go fast through the column, and some molecules get stuck in the column, slow down. And so if the column's long enough, this is why it's so long, if the column's long enough, then you can separate. It's like, you know, if you're at the beginning of a marathon, everybody's there, you know, they're all clustered together. So you don't know, you know, you can't really tell who's going to win, can you? At the beginning of the marathon. But, you know, at the end of the marathon, then for sure you can tell because everybody's going to be spread out. Well, that's the same thing here. You're going to spread out all the molecules, so the slower ones are going to take a long time to hit. And then you get something called chromatogram. The chromatogram tells you, you know, how many molecules of this you have, how many molecules of that you have. And so you can determine the composition depending on how fast it goes through. Is that a physical or chemical separation?
If it's by speed, it's physical.
Yeah, this is a physical. It's taking advantage of what we call intermolecular forces, or attraction. Okay, then for each of these peaks, they aren't sharp peaks like this. This looks like a mass spectrum. It doesn't look like that. It looks like this. These are normal shape here. And so you get these bands or these kind of peaks here. And then this peak gets fed into the mass spectrometer. And then in the mass spectrometer, you can determine it because what you do in the mass spectrometer is you don't just weigh it. If you weigh it, then there are lots of molecules that kind of weigh the same, right? Or might weigh the same or weigh exactly the same. You know, we could have two molecules that weigh exactly the same. Those are often called, not isotopes, they're called isomers. Isomers have the same exact composition but different structures. And so you might have done isomers in those structures. And so, you know, the mass isn't enough information. And so what you do is you shoot little molecules at it. You shoot little molecules to break it apart, to fragment it. And then once it fragments, then a branch hits there and a branch hits there, and then you put together all the branches that broke off of it, and then you can figure out what isomer it is. And so the GCMS is one of the most powerful tools we can use to figure out what the heck it is.
When you say shoot particles at it, did you use alpha particles?
No.
Or did you just shoot
small
like
molecules?
Small
molecules. Alpha particles, you need a radiation source, and you can avoid having an alpha emitter. It's good because you know what polonium emits. You know why those guys die? Alpha particles. Alpha radiation sickness.
Yeah, Professor, I looked it up, like you suggested for Chadwick, and he found neutrons by shooting alpha particles at, let's see, beryllium.
Okay.
He used beryllium.
Yeah. Well, Chadwick, I wonder if he ended up with beryllium poisoning. But anyway, let's go back to the. So that's one way of determining it. But where does this? These mass spectrometer computers have a database. You have to buy it. You buy this database of molecules, and then you know what they do is they take a molecule and feed it through and see what happens. You know, because sometimes it's hard to predict exactly what's going to happen because some things don't go exactly as planned. But anyway, the first thing is we want to know what is the composition of a compound. For example, the composition of water is what? H2O. Well, how do you know that? How is that determined?
Because the hydrogen only has 2 slots for electrons, while oxygen would have more. So
Okay, you could determine it using theory, but did they have theory back when? Is that how they figured it out originally?
No.
No. You know, the way they figured it out is by using some chemistry and trying to figure out how much hydrogen and how much oxygen by breaking it down. Or they could use electrolysis to break it down. But we call that elemental analysis. Elemental analysis will list all the elements present in the amounts. And so it's just a list of elements present and amounts. The amounts can either be a percentage, an intensive, or it could be an extensive, grams. How many grams of hydrogen are there? How many grams of oxygen are there? What's the total mass? What are some instruments for elemental analysis? So let me talk about that. Instruments for elemental. Uh-huh.
We can take a quiz now.
Oh,
How long
that's
do you think
right.
it will take?
Actually, 5 minutes probably. We'll take it in. We're done at 55, right?
Yes.
We'll do it. It's probably. I expect the quiz to take 1 minute or 2 minutes. I don't think it should take more than 1 minute, to be honest. But I'll give you extra minutes.
Alright.
Let's say it's like the last day for it.
Yeah, we're going to take the quiz. Okay, one is XRF. Have you ever heard of XRF? This is what they sent to the moon. They analyze the moon rocks for elemental analysis. Do you know what they do in XRF? In XRF, they shoot X-rays at it, and strong X-rays will knock core electrons off. If you knock core electrons off, then one of the valence electrons will drop back down to fill that core. When the valence electron box drops down, it emits an X-ray. And so what you can do is these X-rays are going to be characteristic for the element. So you'll see patterns of XR. Let's see if we can see a spectrum, XRF spectrum. I'll show you. Our book doesn't really cover it, but I was looking at the AP Chem. AP Chem is really into this. I don't understand why. But you get things like this. It gives characteristic X-rays at different energies, and then you can use that to identify the elements that are present. This came from a 2s core electron from an iron atom. A 2s core electron from an iron atom is different than a 2s core electron from a cobalt atom, that kind of thing. And so we have this. And you can see, core, valence. If you just look at chromium, you can determine that. And so this is XRF. XRF stands for X-ray fluorescence, so it starts to glow, with X-rays. If it's glowing with X-rays, you don't want to be sitting there watching them. But this is what you get. And so elemental analysis lists the elements and the amounts. The tools we can use are XRF. We have something called atomic absorption, AAS. AAS is you dissolve the sample in water and then you feed it. And then different elements will have different colored flames. Have you heard that? Yeah. I was watching TV, and I was just scanning the channels because there's nothing on. And then I saw this guy, with glasses doing flame tests, in a classroom. And then I thought, okay, I'm going to watch this. And then you know what show it turned out to be? Breaking Bad. And then I started watching it then, and then I thought, okay, I'm going to continue watching this because it was pretty interesting. And I watched the whole thing. Yeah, I watched the whole. But it was because of the flame test. Otherwise, I would have just passed it, and I probably wouldn't have ever watched Breaking Bad.
My sister made me watch the ending. I never got to watch the whole show.
Yeah, just the endings?
Yep, just the ending.
You gotta watch the whole show. Crystal growth is pretty big in that show. So I was thinking about that, crystal growth. There's some chemistry. The chemistry consultant is, I think, at UCLA or I forgot, Caltech, one of those. The science consultant. We're going to look at combustion analysis. So let me write that here, combustion analysis. And so this is why we think about combustion and that type of stuff. But anyway, the quiz, I told you I'd give you more than a minute for the quiz. Can you do the quiz on this
Yes.
card here? Pencil or pen? Doesn't matter, I don't care. Pencil or pen. If there are any extras, pass it back. All right, write the formulas for these.